So after solving this, we have our results with us. Let's load this, all the results. Now we can see we have lots of options. So I have created a cut plot to give you the idea, the temperature distribution. Okay. Okay, so this is the temperature distribution on the surface at this particular section. Okay, you can animate it very easily, no problem. You can play it and it will show you how temperature is. Okay, so this will give you the idea where is the maximum temperature along the whole 3D section, or you can say the whole computation domain. Okay, now we can change it to velocity. So and we can see this is the area where we are getting the maximum velocity. Okay, and some of the heat is getting inside. Let's apply some vectors so that we can get more and more idea about the velocity distribution. So this is a good example of applying fan in the system, and then it is going out from this opening. Okay, yep. So we have this option called velocity contour. So we have multiple things like this. We have isolines. We can apply isolines so that we can figure out the values of similar range. Okay, so I'm going to apply it, suppose velocity of similar range. So you'll see, so you'll get the idea that the lines with yellow will have similar velocity, with the green line having similar velocity, and what is the velocity, you will get the idea from here. Okay, and many other tools like vectors to get the idea about the direction of the movement of the fluid on a section. Then we have this option called streamline to figure out where is the turbulence, and you can see these are the areas where we are having more turbulence. Okay, then we have this option called mesh on a section view, so we can even check the mesh. Okay, so that is also available to us. Okay, you can see these areas are having finer resolution as compared to these areas. Okay, so let's go to the contour again, and now let's see the surface plot. We have created a surface plot also, which is very easy. You just have to click on insert, you have to select the faces, select the parameters and the color range, and that's it. So you just have to select the face, like I have to see the temperature on this particular board face, and I want to see temperature of fluid. It could be solid also, but I want to select fluid, and that's it. So along the surface you will have a range of fluid, and you'll see like this, you will get this idea that it vary from 66 to 81 on this particular face. Why I'm saying it, because this option limits me, like the second option limits me to the maximum and minimum of this face only, and not to the global. If you want to see the global values and the color according to that, so you can go to the first one, which is reset to global maxima and minima. When you apply it, it will give you the response as per the global temperature distribution, but this is a better representation to get a clear idea. Okay, so this is one way. So by doing this, I have created few more ways of doing the representation, like this is a temperature distribution of solid on the heat sink. Let me hide this one. Okay, so the fluid is entering, and you will see at the initial contact, these areas will become cooler as compared to the back faces. Okay, so this is giving you a right idea, and you want to see why it is not cooling the back side also. So in that case, you can click on show the flow trajectory, and you will see the fluid is moving upside, like it is coming from here and moving upside. So let me show you what I'm trying to say. Let's play this, let's play this, and you will see it. So it will move upside. So because of that, this is not cooling the back side of this heatsink. So this is first investigation, and we found out that we have to make the position of the fan in such a way that it reaches to the back face of the heatsink also, to make it more uniform. Then we have this option called heat flux plot. So we can select that, and we have this option called heat flux plot. So we can go to the option and we can see what it do. So the purpose of this is to give you the idea that what is the contribution of heat of one component because of the surrounding component. So let me give you an idea what I'm trying to say. So when you select, this is the power source, okay, so this is 18.519 watt power source because of this one. So you can go and see, this is the power supply. So here we apply the 120 Fahrenheit. So because of 120 Fahrenheit, it is developing 18.519 watt, and this 18.519 watt is getting transferred to this, and because of this it is going to transfer into the fluid of the system as well as to the enclosure part, that is the outside body. Okay, so this body is transferring the heat to enclosure, as well as it is transferring the heat to this fluid domain, and that is 6.985. and you can do the calculation. It will be mathematically accurate, it will transfer the 18.51 from by adding this and this. Okay, so when you add this, you will get the same. So this is a conservation of energy, and which is happening here. Okay, in a similar way, this is the main chip which is heating this heat sink with the 3.498 watt, and it is transferring the same. I just selected few bodies. I can select the whole assemblies and sub assemblies, but I selected some limited components to make it simple to understand. This is the capacitor which is generating this much of wattage of heat, and because of the capacitor, the fluid domain is getting the heat of 0.0805 watt as a convection. Okay, so this is a better tool. Plus this capacitor is also heating this whole component by 1.339. so if you are getting some extra heat in the motherboard, sometimes you don't get this idea that where this heat coming from. So this is a better way to check it out, that if it is getting heated, what are the factors contributing that. So that is a better way to find out, and with these visualization you will get the idea who is contributing at what percentage to heat up a body. So this is called flux plot. Okay, so this is it. We will come up with a more sophisticated example which will give you the idea that what are the tools we have in our electronic module. So we didn't use any tool of electronic module yet, but we will see what are the tools we have in electronic module, so that we can target more sophisticated problems in electronic cooling. Okay, so this is it for today. Have a great day.